Good afternoon, everybody. My name is Moti Fania. I'm from Intel, and I'm going to share some of our experience with the work that we've done around IoT. So it's going to be a bit about our insights that we have made, what we have built, and how we have deployed it. So IoT is getting lots of attention, obviously, by everybody. And usually we think of it more in the context of the external world, right? Things, automobiles, gas and oil, many external things that are transmitting to the cloud. We rarely think of it of how it could be beneficial within an enterprise. And this is exactly where I'm going to focus. I mean, we have found that at Intel, there is much relevancy to applying stream analytics or IoT kind of analytics in the enterprise. If you think about it, companies have evolved from the descriptive analytic through the predictive, prescriptive, and so on, but there isn't much investment in the ability to apply analytics on a stream, in the ability to react faster to the data, not after it gets to the database, but when it's being transmitted. Being proactive, being able to close the feedback loop in a much timely manner. And this is something that we believe is a miss, and at Intel we have identified few use cases where we found that it could be highly beneficial. So obviously, manufacturing it's really obvious. I mean, any organization that deals with manufacturing can benefit a lot from being able to collect the data from the machines and apply stream analytics and be able to apply intelligence into this process. In Intel, we are talking about hundreds of millions of dollars, and in order to make our factories smarter, reduce costs, higher yield, and faster time to market, all of this is crucial. But there are other use cases. I mean, Intel, and like many other organizations, is building smart buildings. And you know, it's nice to build a smart building, but if you are not doing something to extract or to implement this intelligence, you won't get much. So being able to get the data from the smart buildings and act to it in near real time is extremely important. Supply chain is another example. Things like asset management and other kind of use cases. And in fact, any machine could benefit from it. I mean, preventive maintenance is the holy grail for such implications or applications, and any machine. It could be air conditioning, it could be anything where you could collect the data and be able to maintain it with much more accuracy and not based on estimates. And in just one use case that we had that is supporting, not the fab itself, not the manufacturing, but the activities that support it, they've identified 100,000 measurements that they do need to collect and do it manually, to think how much this could be improved if you use a platform that can collect all of this data. So usually, this is what we see. I mean, usually when an enterprise tries to implement IoT, they find themselves with, there are many providers, obviously, and they find themselves with a different solution or different platform for different use cases. Each one, in many cases, we are talking about cloud providers, which means that the data will get to each of the cloud providers separately. There is very little commonality between the data, very little interoperability, security risks, and many other negative side effects of having different platforms for different use cases. And some of the assumptions that are hiding in that is that people are thinking of this as, they're assuming that for different domains or different verticals, the needs are so different that you can't really build a common platform, that you can't really have something that can satisfy all needs. So indeed, there are different needs for different use cases or different verticals, but we think that we have found the answer or the formula of what could be a shared platform for IoT. So indeed, there are different use cases, but there are certain needs that all IoT use cases have, and we have identified it both in the work that we have done externally and internally at Intel. And what we have found that there is a certain needs, and it's not just a list of needs, it's a hierarchy of needs, if you will. And usually when you're getting to your customers, It's very rare that you will get, give me the latest and greatest machine learning algorithms. No, usually it will begin with something which is much more modest. Usually they will start by just wanting the data to get and flow into the cloud. I mean, into the data center, into whatever. It could be on premise, it could be on the in the public cloud. So this is one thing, and obviously it's not enough. The next need that we are seeing almost immediately is the ability to see the data, the ability to look on the charts, to be able to see in the eyes that the data is flowing, to see if there are any anomalies, if there's anything that goes wrong. And people like it. This is a way to get trust in the system and that it's doing what it has to do. But you can think, I'm sure that you all understand that it's really not very scalable, right? Who can stare on hundreds of charts day and night, try to sue or to look for something that goes wrong? This is not the way to go for it. And this is why we believe that the next stage is becoming more interesting when we are talking about letting the users, based on their user expertise, based on their domain expertise, define their own rules, where they can define a rule or data monitor on the data and get an alert or an actuation once this rule is met. And it could be a simple rule, like let me know when something exceeds a certain threshold for X period of time, or something more statistical in nature that can involve the mean, standard deviation, and other aspects that are more advanced for some of the users. So this is obviously an advancement, because now you don't have to look on charts, and you can get the ability, self-service, without writing even one line of code, to get something out of the data that you're transmitting. It's good, but again, this is not enough, because we believe that with today's algorithms and machine learning, we can do much more. There is a lot of the detection that we can do automatically. There are anomaly detection, change detection, and other kind of algorithms, and I'm going to talk about a few of them in a minute, that are highly beneficial and can be used by the machine automatically in order to detect some of the anomalies or the changes of the behavior that we are trying to look for. Now, if you consider all of these layers, they could be pretty common to many use cases, right? I mean, think of it, it could satisfy 70, 80% of many use cases needs, and it's quite a bit, okay? You don't have to start from scratch each time. Of course, on top of that, you can still customize or build on top and do some specifics for the use case. This will always be required, but still, we already got to a situation when we can have one single platform that holds all of the data and deals with most of the needs. So now we can go from these silos of approach that is very common to an approach where you have one common IoT platform within the enterprise. All of the use cases can benefit from it. And you can have all of the analytics and all of the goodness that I described before out of the box. In addition to that, you can also even stream it to your favorite cloud provider. I mean, if there is a service that you're getting from outside, you can stream this data through your platform, apply what you want to apply internally, and then stream it further into the service provider. And it doesn't mean that you have to do everything on premise. Although some of the enterprises probably prefer to do it on premise, but you don't have to. You can also continue with any cloud provider that you have. So I want now to share with you some of the considerations that we had in implementing such capability. So obviously, we are not talking about just ingesting the data or moving the data. We are talking about an analytical layer that should allow us to be able to apply analytics, stream analytics, advanced one, on the stream of data as it flows. This is what we want. What it has to be, it obviously has to be scalable. I mean, we want it to be linearly scalable as possible and to be able to deal with the IoT kind of workloads, which could be very, very high and reach high throughputs. It has to be fault tolerant. We don't want a single point of failure, and we want this service to be up. So this is very trivial. However, we have identified 3 more requirements from this capability. First, we want, as I said, to be able to apply analytics on the stream as the data flows, and to be able to close the feedback loop. This is important. I mean, not just to flow the data, but to be able to detect and close the feedback loop, act on it on timely manner, have an actuation based on it. The actuation could be simple. It could be just even an alert, but you want to close the loop very fast. The second one is even more important, because we are talking about the ability to apply effectively machine learning. When you want to have a model, you have to have some kind of acquaintance or prior knowledge about the device that you want to do. You have to have a state. I mean, you can't apply really analytics on a device that you don't know anything about it. I mean, you could, but you probably won't get much. If you could save or have some kind of state or prioric knowledge about this device, I'm sure that you will agree with me that you can apply much more advanced capabilities, and the odds that you'll be able to detect a change or an anomaly are bigger. And the ability to keep this state was an important requirement. And the last but not least is the ability to ease of use, the ability to subscribe very easily to a stream, and to be able to use a language that we are familiar with, Scala, Java, whatever, in a way that we can extract value fast, and last, to be able to deploy it easily anywhere, on-premise, on the cloud, anywhere. So now let me show you how it looks like. I mean, in a high level, the architecture of what we implemented. So basically, we are talking about the traditional IoT use case. You have things, they transmit through gateway. In this picture, there's only one gateway, but obviously you have many gateways. They all send the data through a load balancer to a cluster that we've built, in an on-premise cluster, again, of Korres and Docker. So we have used Korres and Docker in order to host some services that are important for this ingestion layer. Docker, I'm sure all of you are familiar with it. It's a container technology. It allows you to deploy very easily, avoid the DevOps hell. But with Korres, and this is the more important, the more significant piece here, with Korres, we were able to build clusters of these services, which means that we're talking about fault-tolerant technologies, and we want to be able to accommodate. So we got to a situation where we have, even in on-premise, you have the elasticity and the simplicity of being able to deploy many services on a limited set of hardware. In our case, we used Kafka as the broker. I'll show how it looks with Mosquito, Acha as the processing layer, and other technologies for visualization and keeping the time series and the metadata before they get into the storage or container, which is our Hadoop. But Hadoop in this case is much more than a container, because we also use Spark streaming to do some of the processing and the analytics on the data. And I'll explain how we used it. So this is how it looks conceptually, but I think it will be easier to understand it if I show it as a flow. So we're talking here about n number of MQTTs. MQTT is basically the IoT protocol, right? I mean, this is most of the devices know to communicate with this protocol. And the MQTT brokers are usually not very scalable. They're not, and they're not persistent. So what we have done here is basically to put n numbers of MQTT brokers. They don't know each other. All of them are pushing their data into a Kafka broker. It's a scalable broker. It's persistent. From this point, we are in a position where we have a scalable broker, and we know that we are not going to lose any data once it's there. And now we can get the fun stuff where we could apply the analytics. And for the analytics, we have used a framework called Acha. I'm not sure how many of you are familiar with it, but Acha is basically a toolkit or a framework for developing highly concurrent, fault-tolerant applications. It's based on Scala. It implements the actor model, which is a very elegant way for applying processing. I don't know if you heard about it, but you can basically put millions of actors in a single node. And if you have a cluster like we have, you can deal with way more devices and higher throughputs than that. So we have built on top of Acha a framework that we call Pigeon. And Pigeon is basically a capability that allows us to manage this cluster of Acha, apply, get the fault tolerance and persistence automatically out of the box, being able to easily subscribe on a stream, get the data flowing, write a logic in a very simple way, and get benefits like back pressure using reactive stream, and again, the usage of an Acha cluster using the cluster sharding. So it's a very light capability that leverage all of Acha Acha goodness, but in a very, very efficient way, and it allows us to do lots of the analytics that I'm going to describe. And as I said already, Spark streaming is also playing a role in this, in addition to that. I want to emphasize again the use that we have made with Docker and Korres, because I think it's important. One of the aspects that prevents, I believe, many companies from deploying an internal on-premise IoT platform are the challenges of having to deploy such platform internally. Most of the platforms that you have today, the IoT platforms, are cloud-based. What we have found that by using this technology of Docker and Korres, we're able to almost seamlessly, it was a no-brainer to take work that we have done externally and deploy it internally on-premise. And it's extremely important. And beyond that, we could now have the modularity of being able to pick the right services as we need them. So if we don't need Acha, we can deploy a solution without it. We don't need Kafka, the same. You can mix and match the capabilities that you want and deploy only what you need in a very easy way. So this is very important to understand. And Korres is meaningful here, because without Korres, it means that we're talking about single node containers. They're almost useless. You can't do anything with it in a fault-tolerant system. By having Korres, we're able to orchestrate clusters and to use them effectively. So a bit about what we have done for the data monitors. I mentioned that we wanted this first step of intelligence to give the users the ability to define their own rules as a self-service through UI and get the benefits without writing any code. So we've built this capability using Spark streaming. Basically, what we do is to take the subscribe on the streams from Kafka and convert them to aggregated or compressed streams, on top of which we apply the rules. So we have a sliding window, which is basically a sliding window of compressed streams. And based on that, we can apply all of the rules dynamically in runtime. Again, the user doesn't write code. He sets the rule in the UI. They are being kept in the metadata. We use Couchbase for that. And dynamically, we read the rules, apply them on the stream with Spark streaming, and actuate based on what the user defined. It could be an alert. But we basically write it back to Kafka, and from there, all the actuation takes place. Again, the nice thing here, no human needs to take a look to stare on charts, and it leverages the human expertise. But I said that we are basically aiming more than that, and we wanted to be able to apply analytics and not just human rules. And if there is a way to detect things automatically, you want to do it. You don't want to ask the user to define rules that can be detected automatically. So we have implemented a set of algorithms that are relevant for IoT or for stream analytics that are used for all of the use cases. And basically, these are algorithms that allow us to prototype the behavior of devices and to use it in order to apply the intelligence that we care for, which is things like being able to detect changes, anomalies, outlier detection, identify if there are periodicity in the data, and if so, to handle it, and so on and so on. So lots of algorithms that you could basically use for different use cases. So in terms of the analytics layer, I just want to mention 4 specific components that are the most significant for most of the use cases, I believe. The first one of them is, as I said, to be able to detect if there is periodicity in the data. You don't want to alert or trigger an event based on a mistake, because the data, most of the sensors in IoT do have periodicity if you think about it. Temperature, anything, there's some element of periodicity. And you don't want to, because of a change in the behavior that is normal, to trigger an event. But detecting the periodicity is not enough, because you also have to be able to remove it or erase it from the data for the sake of the algorithms. So being able to detect it and then to eliminate it so you can only alert on what is really an alert is important. Change detection is basically a set of algorithms. It's not one, but it's an umbrella of algorithms that allow you not just to detect an anomaly or an outlier, but being able to detect the slightest change in the behavior of a device. And this is important, especially for predictive maintenance. You can't really do anything without being able to detect changes automatically. And sometimes these are even changes that are invisible to the naked eye, to the human. And another thing that we have found here is that sometimes looking only on one sensor is not sufficient. You won't find what you're trying to find, and being able to do a multivariant change detection here is more important. So multi-sensor change detection could be in some cases much more accurate than looking on each sensor individually. And last but not least, being able to detect an alert is nice, but many users can't do much with it unless you're able to explain something about what they get, why they got the alert. It's not always easy, it's not always possible, but being able to use analytics in order to explain why a certain alert was triggered is very, very beneficial when possible. So just to summarize, so we have deployed internally and on-premise one single IoT platform that we are using for many use cases. The platform does leverage our existing big data investments. So I'm sure that many of you already invested in Hadoop or in other big data technologies. The fact that you can use the same investment and build on top of it your IoT platform is obviously a good way to use the money that you already spent. Korres and Docker for the ease of deployment and modularity and avoiding the DevOps hell, and the way it made it easy to deploy on premise. And last, the smart data pipes, the ability to apply analytics in the enterprise, on the streams, in timely manner, proactively, and instead of doing firefighting like many of us do, act on the data in a proactive manner. Thank you very much, and if there are any questions.